Okay. Sorry about that. If you're listening to that, first thing you do when you turn on, go to the, I sneeze into the microphone. Enough to scare you senseless, right? Okay. There we go. Everything's taking about 5 times longer than it should to do. Okay. Finally, we're here. Now, let me go over this one other announcement. You may have heard it last time, but in case Jonathan wasn't here, I don't remember if he was or not, let me go over this. Because second mini-term has started, my Tuesday, Thursday office hours have changed slightly. Not bad, but slightly, just to let you know. Before, on first mini-term, it was Tuesday, Thursday, 10:45 until 12:30. But because my second mini-term physical science class starts a little bit later, now my office hours on Tuesday, Thursday are 10:45 to 1:15. Now, that makes me here later, but it opens up a few more office hours in the middle of the day. 45 minutes more. Okay. All right, any questions on anything we've done up till now? Okay. We were on page 78, chapter 2, 2.4, elementary matrices. And what we're doing here, I have that we had gotten the first 2 of these done. And what it says to do is find a sequence of elementary matrices whose product is the non-singular matrix A. So here's matrix A. I write, and it takes a while for the pen to activate. Okay, and it doesn't activate sometimes, so here we go. -1, -2, and it's writing about half the time. 3, 8. Look at that. Every letter I go to write, okay, that time it did okay. All right, and what we had done, the first thing we did, we multiplied the top row by -1. So the elementary matrix we used for that was what? -1, 0, 0, 1. Okay? The next step we did, and we already have done this, and that was I'll just go on and write them down without actually doing them. So A became when we did that step, that became a 1, 2, 3, 8. Okay? Now, what I was also doing was at the same time that I put E1, I'm going to put E1 inverse. And we did this last time too. What was E1 inverse? Same thing, -1, 0, 0, 1. Anytime you just multiply by a non-zero constant, whatever your 1 was before, it still is. And how you can check this real easily to make sure you got the inverse correct is to multiply these 2 together. And when you multiply 2 inverses together, what should you always get? Identity matrix. And sure enough, you get 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, and 0 plus 1 is 1. Yeah, so you get the identity matrix. That's your inverse, okay? Now, we did the next step, which is multiply, or you tell me. Okay, let me do this. -1, row 1, okay? And what's this? -3, row 1 plus row 3. I should have written that down here, okay? So, what that produced 1, 2, 0. We already did it, so I'm not doing it again. You can go do it on your own if you want to. And its elementary matrix for that one, we'll call it E2. What would that have been? 1, 0. Remember, we used the first row, so we're just using that row. That doesn't change. See, that didn't change going from here to here, so that doesn't change from our identity matrix. And the next, 0, -3. No, you're right. I'm sorry. You were right. -3, 1. Yuck. Can't get my eraser to work. And it's still not working. There we go. Yeah, -3, 1. Sorry, I put it in the wrong place. Now the pen won't work. The system is really bad today, and I can't write. I can't. Okay, -3, 1. Okay, now you tell me what E2's inverse is. Okay, the top is 1, 0. I thought you said -1, 0. Okay. 3, 1. Okay, and if you don't believe it, check it. Okay, and see. 1 plus 3, plus 0 is 1. 0 plus 0 is 0. -3 plus +3, 0. 0 plus 1. Yeah, that works. Okay? Now, that's where we left off, I think, last time. Or did we do the next step? Huh? We did? Well, I erased it and maybe you went home and did it. Okay? Good man if you did. Okay. Huh? Say that one more time. Is that where we were? I didn't remember that we came up with you did everything up to 215. Why did I put my mark there then? Okay, I didn't remember that then we recreated matrix A by the inverses. We had done all those 4 inverses. Really? The brain died somewhere in there. Okay, so let's go on to 215. Sorry about that. I think y'all are just working ahead. Good men. Okay. All right, so let's do 215. Equivalent conditions. Okay? So let's start with A. What do we want to know about A? Square matrix, and we'll call it an n by n. Okay? Square matrix. If that's true, then the following conditions are true. If A is an n by n matrix, the following statements are equivalent statements. Okay? The first of these. Okay? A invertible. Okay. Now, get this. Doesn't mean all square matrices are invertible. It's just saying A is a square matrix. Now, if this next statement, this one is true, that it's also invertible, guess what? If it's not square, it's not invertible. You can't have a square matrix, a non-square, a rectangular matrix, a non-square matrix that would be invertible. It can't be. To be invertible, it's got to be square. So they gave us it was square. Now they're given the condition. If A is invertible, okay, that's one statement. If that's true, the second statement's also true. That A, that same A, multiplied by some vector X is equal to some vector B, has a unique solution, okay, for every n by 1 column matrix or column vector B. Okay? For any one. You can put any B you want to here. That's an n by 1 column matrix. And you can find an X of 1 and only 1. That's what unique means. 1 and only 1 X that makes that true. And no matter what B you put there, you can find it. There'll be different X's for different B's. But for that A, that's only true if A is invertible. Also, if this is true, that guarantees that A is invertible. Okay, those go hand in glove. Okay, number 3. Okay, this follows from 2, AX equal to 0 vector. Now that's a vector now. Now they put, whatever they do. Okay, guess what? It has only what solution? The trivial solution. Now, sometimes you can have this to be true, and you know it always has a trivial solution. But sometimes you have an infinite number of solutions, the trivial solution just being one of them. If A is invertible, then this doesn't have an infinite number, it has only the trivial. Well, that follows from here. Because guess what? That is a solution B, right? All zeros. And this says it has a unique solution. So if that's all zeros, then this is a unique solution, and that is the trivial solution. Now, this also means if this is true, that's true, and that's true. So these all depend on each other. Equivalent conditions. Number 4. Okay? A is row equivalent, remember that's my abbreviation for that, to what matrix? The identity matrix. If you take, and it's identity matrix of size n, okay? If you take that down doing your row reductions, reduce row, all the way down, you're going to wind up with the identity matrix. Okay? Now, frankly, I think I would have started with this one and said, if that's true, then that's true. But you see, they're all true, okay? One true implies the other. But we did this before we even talked about invertible, okay? So, but if this is true, that's true, that's true, that's true. If this is true, that, yeah. Any of those, okay? And then the 5th equivalent condition. A can be written as the product of elementary matrices. Okay. Now that's what you said we finished last time, and I didn't remember finishing it, but we did that matrix A, simple little 2 by 2, and the first thing we did, we proved it wasn't singular. Okay, how did we do that? 2 by 2 is easy. The A on the previous example. How do you? Okay, take a determinant. And that determinant, what is the requirement of that determinant? Non-zero. We did the determinant of that, found out it wasn't 0. We knew then that that was an invertible matrix. It was already square, 2 by 2. When we took the determinant and found out it was non-zero, we knew it was invertible. Then we knew all these things were true. The A could be written as a product of elementary matrices, and that's what example 4 did. It found that product of elementary matrices. And what was that product? How did we get the product? We started the process of doing row equivalence. But as we did each row operation to get to the identity matrix, that's where we're headed. As we did each operation, we did the elementary matrix for that operation. But not just that, we also did the inverse elementary matrix of that one. Okay? Then we got all those down. So we had the row reduction of A, the elementary matrices that made that row reduction happen, and the inverses of those elementary matrices that made that happen. Then what do? We took these inverses in reverse order and found out that A was equal to, I think it was E4 inverse times E3 inverse times E2 inverse times E1 inverse. However many elementary matrices it took to get to the I matrix here, however many it took, you multiply them in reverse order of their inverses, and you can come up with A. That's how we did it. I don't remember doing it, but that's how we did it. Okay. I've done it before, so I know okay. Now, why? What's the big deal with this? Isn't this a lot of blah, blah, blah? It wasn't easier just to do row reduction? Yeah, okay. Well, let's see. There is a thing, it's hard to call it that, a process, no, a presentation that's called an LU factorization. What in the world is that? Lulu? No. What does that mean? At the heart of the most efficient and modern algorithms for solving linear systems of equations. Now remember our little blurbs we talked about? Remember your Google search engines, though we don't know what that one is. It's a linear algebra problem, okay? It's massive. Remember the one about airline pilots and crews and things like that? Thousands upon thousands of equations and variables, okay? I don't want to do those by hand. So they try to come up with efficient ways to do it on the computer. Here's what they found. If you do an LU factorization, you can eliminate tons of steps, okay? So at the heart, look at this, 100% attendance, ding, 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 okay. There were some announcements, you've heard most of them. Just want to let you know my office hours, now that we're in second mini term, have changed ever so slightly on Tuesday, Thursday. I now have office hours from 10:45 till 1:15. Before I was 10:45 to 12:30. Now I'm 10:45 to 1:15. I will try to get that change made to your syllabus and to my locator card in Blackboard, but I ain't there yet. Okay, I've got miles to go before I sleep on that one. Okay, so I'll try to get that done as soon as I can. I wanted you to know it. So at the heart of the most efficient and modern algorithms for solving systems of linear systems of equations, AX equal B, is the LU factorization, in which a square matrix A, so you start with a square matrix A, okay, is expressed as a product. A is equal to LU. What in the world is LU? Okay, well, L is also a square matrix, and by the way, the same size as A, okay, but what that means, it's a lower triangular matrix. That's what the L stands for. Lower triangular. Okay? I'm abbreviating. Which means that all the entries for L, they list them as A's. Sort of wish they hadn't used A's because A is the square matrix we're talking about. But we'll use this since they said it. All the entries here, since it's lower triangular, that should be subscripted. This is for a 3 by 3. If it's n by n, you just keep on going. That all the entries, it's lower triangular, so do the main diagonal. It's a square matrix, so that goes right down the heart of it here. That main diagonal and below are numbers. Requirement of what those numbers are. Everything above that main diagonal are zeros. That's called a lower triangular matrix. And anyone want to hazard a guess what U is? Upper triangular matrix. It would look something like this. Okay? Again, kind of hate they use the same letter, but it's okay. A11, A12, A13, 0, A22, A23, 0, 0, A33. For a 3 by 3, that would be and upper triangular matrix. Okay? You got your diagonal, that can be anything. Numbers up here can be anything. Numbers down here have to be 0. Have to be. Okay? So this is a 3 by 3 lower, 3 by 3 upper. Okay. Now, don't think that those A's are the same. Okay? They're just using that. I wish they would have used like little L's and little U's. That would have made a lot more sense than using A for everything. Sorry about that. For some reason, seems like I'm getting a head cold, but I hope not. All right. So, we talked about it. Let's actually give the definition. You still don't have a book, so let me write it down. If an n by m matrix A can be written if, okay, can be written as a product of a lower triangular, I'm just going to call it LT, lower triangular, matrix L. Okay, from now on it'll just be L, and an upper triangular matrix U, from now on it'll be U, not UT, then, if it can be written that way, then A equal LU, okay, is the LU factorization of A. Okay? Isn't that kind of a duh, you know? If you just said you have a lower triangular matrix and an upper triangular matrix, if you multiply them together and it makes A, then we call it a LU factorization. Well, if you multiply two matrices together to get A, yeah, that's the factorization of A. But this is an LU factorization of A. Now, part of the deal here is that you might be able to have any old two matrices multiplied together to give A's. But if they're not upper and lower triangular, then they're not LU factorization. So in other words, A may have several factorizations, but if you can find one that the left-hand one is a lower triangular, the right-hand one is upper triangular, and when that produces A, you call that the LU factorization. So let's do example 5. I don't think I'll need the room, but just in case I do, let me start with a clean slate here. Sorry. Here is a matrix. 1, 2, 1, 0. Is that upper triangular or lower triangular? No, neither one. Okay? Has a 0, but it's not in the right place. Okay. But it's a matrix. It's a square matrix. Well, let me ask this. Is it an invertible matrix? We haven't said anything about that, but just to give you the question, is it? Why? The determinant is 2. It's not 0. It's actually minus 2, but yeah. Okay? It's not 0. That's the deal. It's not 0. Okay? Now, we haven't said anything about that. Okay? Now, I really don't like this too much because what they do, they just tell you this is 1, 0, 1, 1 times 1, 2, 0, negative 2. Now that's a 2. For some reason the pen skimmied, but it didn't erase either. Okay, well, all right. Let's see if we can make that 2 look more like a 2. Okay. Now, They didn't tell you how they came up with these. But what can you tell me about this one? Yeah, there's a 0 in the upper left corner. It's a lower triangular matrix. How about this one? Second? Up, lower, upper. That's upper triangle. The numbers are in the upper triangle. Here the numbers are in the lower triangle. Lower triangle matrix, upper triangle. In other words, anything above the diagonal here is 0. Everything below the diagonal here is 0. The 2 by 2, it's only one number, but it still is. Now, they just told you that was true. What? I don't believe them until I check it. I'm not very trusting, okay? So let's check it and see if indeed that's true. It's 1. Okay, they got the first one right. How about this one? Well, okay, they lucked out there. They got 2 out of 3. Okay, how about this one? And it's still 1. Okay, really lucky. Okay, here. Hey, yeah, they got it right. Shucks. Okay, we found, or they found for us, this is a matrix. That is a square matrix. It can be written as a product of a lower times an upper triangular matrix. So therefore, this is a LU factorization. So this would be what we call matrix A. This is what we call matrix L. This is called what we call matrix U. A is equal to L times U. Okay? Now, you might say, so? And that's a very good question. And they do the same thing with the next one. Let's do it. It's going to take a little bit longer to check, but let's do it. Okay? A is equal to, this is a 3 by 3, 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Okay? Now, this is not nearly so easy to say, yeah, that's an invertible matrix, but we really don't care about that now. Okay? Yeah. Okay? It's just a 3 by 3 matrix. Their claim is that you could get that matrix by multiplying 1, 0, 0, 0, 1, 0, and I can't read it. Here it is. 2, negative 4, 1. Okay. Now, I kind of don't like the way they're doing this, but it's all right. What is that matrix? A feature of it. It's a lower triangular matrix, and this one, they claim, is 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. Okay, finally. Okay. Now, I don't know anything else about it now except it's a upper triangular matrix. Now, the deal is they claim that that is a product. Okay? I'm a cynic, so I kind of don't trust them. Okay? Now, I'm going to point something out to you so far. Not going to say it's always true, but, and I don't think it is always true. I think it's only in certain circumstances. It sort of was bugging me a little bit, but if you look at the first one that I already erased, I wish I still kept it up there. For the lower triangular matrix, they didn't change the top row. I'm sorry, they didn't change the first column. Okay? but other things changed of the lower triangular matrix. Of the upper triangular matrix, it didn't change the first row. Now, frankly, I think that's only because you have a 1 in both of those places. So if you look at this one, though, here's the matrix, and we haven't proven this yet. But look, the first column stayed the first column, and the first row stayed the first row. I think the reason for that is a leading 1. I'm not just going to swear to that, but I believe it is. I think if that wasn't a leading 1, you might have some difficulty with it. Okay, but it's just something to note. This may make life a little easier later. No guarantee, but it's just an observation. What's that? Okay, second row. Second row of this one stayed the same. The second column of this one, though, did not. Okay, so can't carry it too far. Okay, but yeah, in that chance it did. But I think the reason is this was a 1. But when you try to do it the other way, I believe because that's a 2, I think that's sort of messed up your other thing. So, yeah. I'm not going to say that will always work at all, but it was just something worthy of note. Maybe a pattern, it may be a coincidence. Let's see. Let's do it and check and make sure we got it right. It's going to be 1. Ah, that's pretty obvious. This one. So that's got to be a -3. Yeah, it came up 0. Now, I think you'll see this because you're multiplying, because this is that's going to reproduce this row, guaranteed. But if this hadn't been a 1, if that hadn't been a 1 there, would it still have done it? There, we don't know that answer yet. But I said that's, I think, because that's a 1 there. Okay, we got the first row. How about the second? Sure enough, it is a 0. That? Oops. Okay. I think because there's a 1 there, that had to duplicate this row. So no surprise there. If that hadn't been a 1, it probably wouldn't have. Okay? How about the third? Yeah, that's, again, you got, your 2 there, and that almost was guaranteed because of that 1, but we don't know for sure. Let's go on. Which one were we on? Third? Yeah. Okay, this one. And that adds to -10 plus 0 is -10. And plus 14, 2, yeah. So that did work. Okay. So again, I sort of pointed that out. It was in all examples, but I'm not saying it's a pattern yet. Okay. So sure enough, that is a lower triangular matrix multiplied by upper triangular matrix produce A. Yep, that's a LU factorization. All right. There's another little linear algebra applied down here. Computational fluid dynamics, CFD, sounds like a disease or something, is the computer-based analysis, and now that y'all have had 151, y'all can do this, right? Yeah, I'm just kidding. Okay, of such real-life phenomena as fluid flow, heat transfer, chemical reactions, solving the conservation of energy, mass, and momentum equations involved in the CFD analysis can involve large systems of linear equations. So for efficiency in computing, the CFD analyses often use the matrix partitioning and the LU factorization for the algorithms. Aerospace companies like Boeing and Airbus have used CFD analysis for aircraft design, because guess what you're dealing with there? Fluid flow, the airflow across the wings, across the ailerons, across the rudders. They do all this so they don't have to build prototypes and see if they work. Nah, that doesn't work. Let's build another one, change this. They can do it with equations. They can do it with a computer and do their design on that using their equations. But every time they change something, they've got to do through analysis. So if you can find the techniques that are very efficient, cut down your computer time. Okay? Computer time does cost, by the way. Okay? For instance, the engineers at Boeing use CFD analysis to simulate airflow around the virtual model of their 787 aircraft. Is that the Dreamliner? I don't remember. Is that the Dreamliner? Okay. To help produce a faster and more efficient design than those of earlier Boeing aircraft. It makes you wonder. Those earliest planes, how many iterations did they have to go through before they got it right, you know? Now with computer design, you can eliminate a lot of that really expensive redesign, rechange, you know, stuff like this. I don't know if you've read much about World War II, but there is a great, it's a true story. And it's the name of the book is, they made a movie out of it. I can't remember. Not Unvanquished or something. It was the story of a guy who was in a bomber, American pilot in a bomber, American-made bomber that they just sort of threw together without going through lots of testing. That plane was a death trap. They lost so many of them because it would just have all sorts of failures. That's because they were producing them before they had tested them well enough. Thank goodness we don't live in that era anymore, you know. So linear algebra, pretty important stuff. Okay. But anyway, he was shot down, or the plane crashed. He was stranded in the ocean for a record number of days, he and one other. There were 2 or 3 that survived, or 3 or 4 that survived. One died while they were on the raft. 2 made it out, and they were rescued. Does that end the story? No, he was rescued by the Japanese. So he went to a prisoner of war camp. And then the story continued there, and he was there till the end of the war. It's a fascinating story. I can't remember the name of it. I'll think of it midway through the next class or sometime. Okay. Now, top of the next page. If a square matrix row reduces to an upper triangular matrix U using only row operations of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization of matrix A. So we start with the upper triangle, which is a bit bizarre, but they do, okay? Okay? All you need to do is keep track of the individual row operations as shown in the following example. This time I read before I erased. Okay, I'm catching on, folks. Okay, what we're going to do is take this matrix here. I'm going to erase it so you can't cheat, okay? And let's do row reduction on it. Now, what's our target here? To get it in what form? Say again? We want it in upper triangular, okay? So, what do we want to do? And this is a good choice, it looks like, because look there. You got a 1 there, that's what you wanted. You got a 0 there, that's what you wanted. All we got to do is get a 2 there. So what's your first step? -2, row 1, plus row 3, sorry. Okay? Now keep up with it, okay? Now it says keep track of the individual row operations. Okay, so you tell me what that's going to produce. Row 1 stays the same. 1, negative 3, 0. Not too surprising. Row 2 stays the same. 0, 1, 3. Not too surprising. What does row 3 become? 0. I can't hear it, sorry. Negative 4, is that what you said? Okay, negative 4. Okay, my hearing's bad. And 2, okay. Now, are we upper triangular yet? Not quite. What do we need to do? Oh, and by the way, let's go over here on the side and here's how we keep up with our operations. We have it written there, but that's not good enough. We have to write the elementary row operation. So what elementary row operation is equivalent to what we just did? Okay, 1, 0, 0. That didn't change, just like that row didn't change. 0, 1, 0. That didn't change because we didn't change anything there. Negative 2, 0, 1. All right, there's our elementary row operation. And guess what else we're going to have to do? The inverse. E1 inverse is going to be what? Yeah, 1, 0, 0 doesn't change. 0, 1, 0 doesn't change. What's that? What did I just do? What, to get to this first one? This one? Okay. We did this operation here. Okay. This might be helpful. Glad you asked. Okay? We started with matrix A here, and we did the first step of row operation, row reduction. You got that? Understand that? Okay. So let's imagine we're starting here with an identity matrix, same size, I3. So we're going to do that same element, the same row reduction on that one to get our first elementary matrix. Okay? So what we're going to do is negative 2. Okay, we're going to write down the first row just like we wrote down the first one there. Write down the second row just like we wrote down the second row there. And then only operate on the third and do negative 2 times 1 plus 0 is negative 2. Negative 2 times 0 plus 0 is 0. Negative 2 times 0 is 0 plus 1 is 1. That's how we got that. Okay. That's called the elementary matrix that did the same thing as the elementary row operation. Okay? Now the next step is finding the inverse of that elementary matrix. Okay? Now, remember what they said. As long as the only steps you use are multiplying one row by something and adding to another row. We're not changing signs, we're not switching rows. We're only doing that operation. Okay? So, what's our next? Well, what is going to be the inverse of that matrix? Anyone remember what the little deal was? It's what? That becomes a positive 2, 0, 1. The top two don't change because they didn't change before. And how you can check this and make sure that you got it right is to do your multiply these two together, you should get that. Okay? 1, 0, 0, that's a 1. 0, 0, 0, that's a 0. 0, 0, 0, that's a 0. 0, 0, 0, that's a 0. 0, 1, 0, that's a 1. 0, 0, 0, that's a 0. Yeah, everything's done okay so far. It's this last one that's going to have potential problems. What does this give you? Negative 2 plus 2, that gives you a 0. And then 0, 0, 0, that gives you a 0. 0, 0, 1, that gives you a 1. So sure enough, we got the identity matrix again. So yeah, that's the right elementary matrix. Okay. What's your next? Now remember what our goal is? All we're interested in is upper triangular. So all we want is that -4 to become a 0. How do we make that happen? 4 times row 2 added to row 3. All right? I think we'll be ready now, won't we? And this will be, we're not doing anything to row 1, 1, -3, 0. Not doing anything to row 2, 0, 1, 3. But what's our new row 3? 0, 0, 0, 14. Okay? Now, what elementary row operation did we do there? Oh, this is E2. Okay, now, here's what you don't do. Don't use this one. Go back to your identity matrix. And you do that on here. So what would be this row operation, not on E1, but on your identity matrix? What would that be? What? You do the easy ones, don't you? Yeah, you did it again. Okay, and what would this one be? 0, -4, 1. Okay? Okay. Remember when this, I'm sorry, you're right. I was doing the next step. Okay? I was doing the inverse. Okay. Sorry, my brain jumped ahead. No, you're right. It's a 4 there. Okay? And this one would be, this is what I was doing. 0, -4, 1. Sorry, I jumped on ahead to do that. Okay. All right. And you can go back and check that, and you'll see that those turn out what you want it to. Okay? Now you've got an upper triangular matrix. Now, what their little statement here is, if a square matrix A reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row, okay? Only that operation. By the way, that'll always be a row below it. Then it is relatively easy to find the LU factorization. We found the U, I admit, we got that. We haven't found the L, okay? How do we go about finding the L? Okay? Now, here's what we do, okay? And this takes us back to what we did before, and I really wish we had more room. If it's okay with you, I'm going to erase the identity matrix because we know what that is, right? Is it all right to erase it? Okay. If it'll let me erase it. Okay, there we go. Now, here's the deal. Okay? Notice they didn't tell us to do this, but I said we're going to have to anyway. So we got the inverses. Remember, we do those in kind of reverse order, right? It looks like it's the right order now. We take this one, E1 inverse times E2 inverse. Okay? Now, let's do that. Let's multiply those two together. Okay? And they're over here, but we can do it over here, can't we? I just don't want to write it again. I won't ever write the answer. They will multiply. 3 by 3 by 3 by 3 is going to give us a 3 by 3, right? Okay? So let's do it. These are pretty easy because they're pretty simple matrices. This one times this one. E1 on the left, inverse on the left, E2 on the right. Okay? Okay. I think that comes out of 1, doesn't it? Okay? do 1, 2. Whoops, yeah. So that came out as 0. Okay, 1, 3. Okay, that came out as 0. Okay. Okay. Yeah. All right. Next, 2, 1. 2 here, 1 here. Got 1 here. Okay. Goodness, y'all are all a bunch of. I mean, no. Seems like they have a bunch of zeros here, don't they? Okay. Let's do 2, 2. 2 here, 2 here. Okay, we finally got a non-zero there. 1. And 2, 3. A lot of nothing here, isn't there? Okay. How about 3, 1? 3, 1. Well, at least it's not a 0. It's a 2. And 2, 3, 2. -4. And the last one we've been waiting for. Whoops. It's okay. 1. Okay. Now, if y'all have been taking notes, I want you to notice what this was in our last example. We noticed that this was what? Upper triangle. And notice that was the upper triangular. That was the second end of this one. I wish I could have left all that on the board, but I couldn't. I didn't have room for it. Okay? But now, just doing this, identifying the elementary matrices that did that, and the inverses of those matrices, and then multiplying those together in that order, what have we got here? A lower, and look at the previous example. Is that the same lower triangular matrix we had here? Yes, it is. So all you had to do was row reduction of this to get this, while you're identifying elementary matrices that were really simple, and their inverses, which was pretty simple, and then multiplying together, which was pretty simple. That gave us our lower identity matrix. So now we've just taken this matrix, and by doing one row reduction, gotten an upper identity. While we did this upper triangular matrix, while we were doing it, keeping up with the elementary matrices that these steps included, and their inverses, both of those were easy steps. Multiply those two together, which was easy step, and you came up with the lower triangular matrix. So this produced our upper, this produced our lower, and we've just now factored A into an upper and a lower matrix. I didn't know we could factor matrices, but we can. You've just done it. Okay? Now, and again, so what? And you're sadly telling me, I could tell the sadness on your face, we were out of time. I apologize that we were so late getting started because I got tied up helping people find classrooms and stuff. We will start next time. I think I've gone over that several times. Well, no. We'll start off at the paragraph at the bottom part of that page, and we'll go from there next time. Oh, homework exercises. You weren't going to let me get away without that. Okay. Any of the odds 1 through 7? either 9 or 11 or both, either 13 or 15 or both, 17, any of the odds 17 to 21, 23 or 25 or both, 20, any of the odds 27 to 33. You can do the true false 35. Think about 37. Try to do 39. It's a doable problem. And then do either 31, 41 or 43. And we'll pick up from there next time. Good deal. We'll see you later today. I was going to say have a good weekend, but you can't yet. Okay.
Can I bring the paper for this class?
Sure. Yeah. No, you have to bring it for the right class, though, anytime you want to.
Okay,